All right, our last two vector lessons have to do with finding intersections between these things we've been dealing with. So we're going to start with lesson 9 is points of intersection involving lines. So we're going to see how 2D lines cross with 2D lines, how 3D lines cross with 3D lines, and we're also going to see how a 3D line might cross with a plane, all in lesson 9. And then lesson 10 is the big one. It's about planes crossing with other planes. So whenever I start a new type of intersection, I like to think about what possible scenarios there could be. So in 2D, when you have two lines, those lines might have a POI. They might be parallel. Or I might give you one equation and then another equation that are in fact the exact same line. So the fancy math word for that is coincident, which means they're the same line. And we'll say that this one has one solution. There's one point in common between those two things. Parallel has no solutions. There's no points in common between them. And coincident has infinitely many solutions. Now in 3D, all of those same things can happen. We can have 3D lines that cross for one solution. We can have 3D lines that are in fact parallel and no solutions. We can have 3D lines, I don't know what I'm doing to keep doing that, but it keeps happening to me, that are coincident and have those infinite solutions. In 3D, there's one other case, so take a second, think about it. There's one other thing. If the lines are in 3 dimensions, there's one other thing that can happen. And what it looks like, well, it's very tough to draw in 2D what it looks like. Well, maybe I'll try and draw a set of axes. We'll see how bad I do. Maybe I'll... So let's say that line's crossing there and there. And we'll say that line's crossing here and here. So different spots on those planes. And they just kind of miss each other. There's some space between them. So two lines can be not parallel, but also not touch each other when there's 3 dimensions. We can kind of use the depth to make them miss each other. So think about, pretty easy to do, just cross your arms in front of yourself like an X, but don't have your arms touching. Your arms are not parallel, but they are also not touching. So the fancy math word for that, these lines are called skew lines, which means they're not parallel and also not touching. So no solutions there. The other way you can think of it, draw a line on your ceiling and then a different line on your floor that aren't parallel to each other. Those two lines aren't going to cross unless you're in a really weird room. So those are called skew lines. So 3 things can happen in 2D, 4 things can happen in 3D. So we're going to see what it looks like in 2D first. So I like to first look at the equations I'm dealing with, so I can see that these are lines. I can see that it's 2 dimensions just by the style of equations. The first line has a direction vector of 3, -2. The next one has a direction vector of 2, -1. So those are not scalar multiples, which means we're not parallel. And if we're not parallel, we're definitely not coincident as well. Which means these lines will, because we're in 2D, they have to cross. They're not parallel. There's no depth to miss each other. They're going to have to cross. So what I do is I like to start with the parametric equations. So I'm going to write out the parametric equations of each line. I think I got it there. Just double check before I get too far into this. Yeah. So one thing you'll notice is I have used different letters for each line. They need to be different letters. If they're the same letter, you're not going to be able to solve for the point of intersection, because the parameter, what I plug in, which k value I use to get the point on this line, can be different than the t value I need to use to get the point on the first line. So they need to be different letters. If I was trying to be tricky and put them both as T, you have to know to change one of them to a K. But I usually don't do that. I'm usually not that tricky. But if you're making the equations yourself for some reason, like I give you some points and you have to first craft the equations and then come up with the point of intersection after, know to use two different letters in your equations. So from there, it's pretty simple. We've got an X here and we've got an X here. So we can just do some grade 10 substitution. If those x's are going to be the same at the point of intersection, then those values, the right sides have to be the same. So I'm taking this really and subbing it in there. And I'm going to do the same thing. Take this version of y and sub it into the other equation. So -2 minus 2t equals 4 plus k. There we go. So that takes my 4 equations with 4 variables that we started with. And now we have 2 equations with 2 variables. So that's nice. We often get so many equations, I like to number them. So the first one's equation 1, the second one's equation 2. Just a communication thing. And I'm just going to do some grade 10 substitution. So I'm going to look at these two things. I got to solve one of them for one letter. Looks like number 2 is going to be the easiest to solve something. So I'm going to say 2 implies, so that's like an equal sign with an arrow, or just a normal arrow, that k is, if I move the -4 over, I'm going to get -6 minus 2t. And then I can sub that to equation 1. And so we're going to get 11 plus 3t equals -5 plus 2 times -6 minus 2t. Passing that 2 through, I'm going to get -12 with the negative and 5 in front. We get -17 and then -4t. Okay. And then I'm going to whoosh the t's to the left side. So it's going to be 7t when I move the -4 over. I'm going to whoosh the other things to the other side, the 11 to the other side, and get -28. Divide by 7, divide by 7. I get t is -4. And if t is -4, then k is going to be -6 times. So I'm looking back up at this equation up here, plugging the -4 into there. So that's 8, that's 2, I believe. So I actually didn't need to find k, and we're actually not done the question, because the question is find the point of it, the point of intersection. And the point of intersection is going to be the x and the y. So actually with the t, what I can do is go back to line 1 and say x is going to be 11 plus 3 times -4, which is going to be 11 minus 12. I don't know why I'm all of a sudden showing so much work when I was skipping all the work before. You don't have to show all these calculations like that. And y is going to be -2 minus 2 times -4, which is going to be 6. That's better. So we get the So you can do it just in 2D, you can do it just with the t value. Once you find one value, you can get the point of intersection, because in 2D, you know that it is a point of intersection. You know that if they're not parallel, then they will have to cross. I can use this k that we chose as a check if we want, but this would kind of be optional. -5 plus 2 times 2 is, -1, that's good. The y is going to be 4 plus 2, which is 6. Okay, that's good. So I get the same point on both lines. So that's a good check. In 3D, since they can be skew, they can be not parallel and still not cross each other, you actually do have to get both variables and check to make sure you in fact get the same point on both lines. So I'll show you what that looks like, I'm sure, in the next example if I plan this lesson out well. Okay. So find the point of intersection between the following lines. If they do not intersect, state whether they are parallel or skew. So the first line has a direction vector. If I'm reading that out, it's the thing with the t's. So that's the first direction vector. The second direction vector is 2, -1, 1. I can eyeball those. These are not scalar multiples, so therefore not parallel or coincident. So we're down to either these lines are going to cross and have a point of intersection, or they're going to miss each other and be skew with each other. So I'm going to do my substitution. I'm going to set the x things together. And we now have 3 equations. We have 3 equations, but only 2 variables. So that's actually what allows, mathematically, that's what allows for the skew, for it to not fully cross. You can make the first 2 equations happy, but not make the third equation happy with those same values. That's what's going to allow for the skew mathematically. We've got this extra equation we have to satisfy at all the same times, and maybe it's just not possible anymore to make all 3 happen. So I'm going to pick one of these equations that's easy to solve for a letter. And I don't know, number 3 looks pretty good to get k by itself. So number 3 implies that k is going to be -2t plus 8 when I rearrange that equation. And then I'm going to choose to sub it into one of the other equations. So I can sub it into 1 or 2, doesn't matter, and solve for t. I'm going to go ahead and sub into 2 because it's got 1k instead of 2k, so maybe that'll be easier. So I'm going to say sub to 2 and say 1 plus 4t equals 3 minus, in brackets, -2t plus 8. Maybe I'll zoom up here as I solve this. So on the right side, I have a positive 2t. I'm going to swing that to the left side and subtract 2t from the left side. So I'm going to get 2t on the left side. On the right side, I have 3 minus 8, which is -5. I'm going to swing the 1 over, make it -6. So that's just rearranging that equation. If you need to show the work, you can show the work. But if you can think it out in your head like I just did and not make mistakes, like I hopefully didn't, then go ahead and do it that way. So t is -3. So once we have t, we can find k using this equation here. K is going to be -2 times -3 plus 8, which is 14. 14 for k. And at this point, we don't know what's happening. We still don't know if they're skew or if it's a point of intersection. And the only way to check that is to actually go to the lines and try and figure out what we have with the variables we have. So I'm going to go to line 1. I'm going to plug in -3 for t. So x is going to be -1 plus 3 times -3. So that's -9 plus -1 is -10. Y is going to be 1 plus 4 times t. So that's going to be -11. And then -2 times -3 for z is going to be +6. And line 2, we're going to plug in the k value we found, which is 14, and get x, y, z. And what I'm going to do is to build suspense. I'm going to start from the bottom up. So z is -8 plus 14 is 6. Oh, that matches. That's good. Y is 3 take away 14 is -11. Oh, that matches. This is looking pretty good. X is going to be -1 plus 2 times 14 is 28. So that's 27. And we see that these lines, in fact, have missed each other. This is not the same point on both lines. It is different. So point doesn't match. Therefore, these lines are skew, which means there is no point of intersection. There is no solution to this. And I knew the way I had done it that I was going to get. So you usually get 2 points that match if you kind of follow my steps. You get 2 coordinates that match, and it's just the third one that's going to miss. I knew it was going to be the x that was going to miss because if I look back at my work, I used equation 3, which was the z equation, and I subbed it into equation 2, which was the y equation, and I never ever touched equation 1. So since equation 1 was the extra equation in this, the way I did it, I knew that if it was going to not match, it was going to not match in the x coordinate. So you don't ever have to think about that, but that's how I knew to build suspense from going the z to y to x. So I made the bottom 2 happy, but not the top one. So that's what it looks like when they're skew. And if it was a point of intersection, we would have got a perfect match in all 3 spots. So we're going to shift gears, and we're going to think about now a 3D line and a plane. So think about, see if you can draw out the different cases. You have a line and a plane. What ways can those things interact? I'll give you the clue that there's 3 different things that can happen. So the first one is you get a point of intersection. The line crosses the plane. The next thing that can happen is the line's kind of parallel to the plane. So this has one solution. This has no solutions. And the last thing that can happen is that that line is actually sitting on top of the plane. So that's like the plane is your floor and the line is drawn along your floor, and that would be infinite solutions. Every point on the line is a point of intersection between the 2 things. And there's no like skew option here. There's no way for the line to miss the plane if it's not parallel, because again, the plane goes forever and ever in all directions. So there's no way to get around it for the line if you're not parallel. So those are the 3 options that can happen. You're either going to cross, you're going to be parallel, or you're going to be sitting on the thing and always connected. Now, I like to start out and see, well, which solution do I have? So when we have planes, we're always going to want the scalar equation of the plane in these types of problems, in this lesson and the next lesson. So if you ever started with a vector equation, if I was ever mean, the first thing I would do is change the vector equation into the scalar equation. I would cross the direction vectors, get my normal, plug in the point, solve for d, because it's just so much easier to work with the scalar equation in these sense. And so what's going to happen is we're going to know the normal vector, and we're going to know the direction vector for the line. And if the line is parallel to the plane, that's also, the line's going to be perpendicular to the normal vector of the plane, right? If the normal vector is sticking out at 90 and then the line is in the same direction of the plane, it's going to cross that line at 90 degrees as well. Same thing's going to happen here. If the line's on the plane, then it's going to be perpendicular to the normal vector. And this one, the normal vector sticks out, but that's not 90. So we'll be able to distinguish whether it's a point of intersection, or at least whether it's one of these 2, by looking at the normal vector and the, so case 1, if you take the normal vector and dot it with the direction vector, you won't get 0. And for cases 2 and 3, the normal vector is going to be perpendicular to the direction vector, so the dot product will be 0. So you can kind of check before you start whether it's going to be perpendicular or not. And I'll also show you a way that if you don't want to do that check, how to tell what happens if you just foolhardily go and try and find a point of intersection that's maybe not there. So this one, the normal vector is 2, -1, 6 on the plane. That's the ABC on the plane. And we're going to dot it with the direction vector for the line. And we're going to get -2 plus another -2, so -2, and then +6, and that is definitely not 0, that's 2. So therefore, we know that we have a POI going into this. We know it's a single POI because the normal vector and the direction vector are not perpendicular to each other. And again, I like the parametric equations for the line. We have those, and guess what? The plane has an x, it has a y, it has a z. So I'm just going to plug those in for x, y, z. Can't see my signs anymore. Plus 6 times. And now we just have a single equation with one variable. So we should be able to get k pretty easy. So 8 minus 2k minus 6 plus 2k minus 12 plus 6k plus 14 equals 0. What are we left with there? Looks like 6k because the minus 2 and the plus 2. And then for numbers, we get 2 minus 12 is negative 10. Plus 14 is positive 4. Swing that to the other side and get negative 4, I believe. And I'll just double check before I make more mistakes in this video that I have to edit out. Yeah, 4 on that side, so negative 4 on the other side. Divide by 6, divide by 6. Get k is minus 2 over 3. And once we know k, the easiest thing to do is get the point from the parametric equations of the line. So 4 plus 2/3 for x, 6 plus 4/3 for y, so just plugging k into the x, y, z over here, negative 2 plus 2/3. So 4 is 12/3, so that's 14/3, 6 is 18/3, so that's 22/3, and that's negative 6/3 plus, so that's going to be negative 4/3, I think. That's my point. Therefore, POI is 14 over 3, 22 over 3, and negative 4 over 3 if I didn't mess up any of those fractions. And if I did, just pretend I didn't. Okay, so that is what it looks like when it's a point of intersection. The next two are what it looks like when it's parallel and when it's on top of. So I'm going to have those two examples. There's 3 cases. There's 3 examples. Guess what? I picked one of each. So I'll show you what that looks like next. All right, so let's take a look at this one. Just going to get rid of that circle there. So the direction vector of the line is 1, 2, 2. The normal vector of the plane is 2, 3, negative 4. If I start with the dot product here, I get 2 plus 6 minus 8, and I get 0. So I know that the direction vector is perpendicular to the normal vector of the plane. So I know, therefore, it's either parallel or coincident on the plane. So one of those two things is happening. So the line and the plane either have every single point in common, well, every point on the line is a point on the plane, or none of the points on the line are on the plane. Those are the only two options. So the only thing I need to check, actually, if I know that, is one point on the plane, or on the line, sorry. If one point on the line is on the plane, then they're all going to be on the plane because of this perpendicular normal and direction vector. And if one point on the line is not on the plane, then none of them will be. It'll be perpendicular. And one line we know, or sorry, one point we know for sure is on the line is 5, 4, 7. That's our starting point. So all we have to do is try 5, 4, 7 in the plane. So the left side is going to be 2 times 5 plus 3 times 4 minus 4 times 7 plus 7. 10 plus 12, take away 28 plus 7. And that looks like the positives are 29 and the negatives are 28. So that's 1, which is not equal 0. which it should be because that's the right side of the plane. So that means 5, 4, 7 is on line, but not on plane. Therefore, since we've already done the analysis, we know that the line is parallel to the plane, and we get no solution. Now, the other way to go about this, if you don't want to check, if you don't do this check first, and you don't know which case you have going in, the other way is just treat it like the last example. Just plug in the line into the plane. So 2 times 5 plus k plus 3 times 4 plus 2k minus 4 times z, which is 7 plus 2k plus 7 equals 0. So that's the equation you'd get when you plug in. And you're going to get 10 plus 2k plus 12 plus 6k minus 28 minus 8k plus 7 equals 0. And you're going to see that the k's are going to disappear. So you get 2 plus 6 is 8, minus 8 is 0. So you get no k, and you get 29 minus 28 again. So you get 1 equals 0. And this is just simply not true. So you get an equation that's not true. So you're plugging the line into the plane, and you get this impossible equation, so you know that they don't cross. So you would know that they would be parallel. So that's the other way to go about this. So you can either analyze the direction vector and the normal vector and see if it's the dot product 0, and if it is, then you know just try the starting point and see if it works. And if it's not, you'll get an impossible equation if it's parallel. And then we'll show you what happens when the line is on the plane. So I'm pretty sure this line is on the plane. So I'll start out with this one. We'll do the direction vector dotted with the normal vector. We'll check first, but I'll show you the other way to do that. You get -3, sorry, I guess I should write out the vectors. -1, -1, 1, dotted with 3, -1, 2. And we get -3 plus 1 plus 2, and that is 0. So we can conclude parallel or coincident. And again, same sort of idea. All we need to do is check the starting point. So we're going to do 3 times 2, this is the left side, minus 14 plus 2 times 1 plus 6. So we get 6 minus 14 plus 2 plus another 6. That looks like it is 0, which is the right side. Therefore, 2, 14, 11 is on, not 1, is on both. Therefore, this line lies on the plane. So that's the first version of this problem. You know what, I'm just going to erase it so that I don't have to do that weird zooming back and forth. So that's the first way to do it, where you check first and then just check the point if you know it's one of the two weird cases. The other way, I'll show you what it looks like the other way. The other way, you just foolhardily jump right in. So 3 times x, which is going to be 2 minus k if you wrote out the parametrics, minus y, which is going to be 14 minus k if you write out the parametrics for y, plus 2z, which is 1 plus k plus 6 equals 0. This is the equation we get. And we get 6 minus 3k minus 14 plus k. It's a 14, not a k. I was getting myself confused. This is the k. So you have -3 plus 1 plus 2, and the k's all go away, which is not okay. And we get 6 Take away 14 is -8, plus 2 is -6, plus 6 is 0. We get this equation of 0 equals 0, which is always true. So when it was parallel, we got 1 equals 0, or just some other number equals 0. It doesn't have to be 1. And that's never true. Doesn't matter what k is. Here, doesn't matter what k is. 0 is always 0. So therefore, line lies on the plane. We tried to find points that are on both, and we found that any k value would work technically. So that's the other way you tell. So you choose whether you want to do the dot product method or just plug in and see if you get one, like a number equals 0 versus 0 equals 0, and just remember which one's which. Totally up to you. So lots of practice for this one, I'm sure. So yeah, we'll get at that